This is a video for Chapter 9. This is a fairly short chapter where we use some of the methods described in the previous chapter, mainly laws of large numbers and central limit theorems, to analyze the properties of the OLS estimator. Okay, so before, recall when we did the distribution theory for beta hat, we assumed fixed regressors. Which means we're just treating the x's as constant. Now we're going to treat the x's also as random variables. So this means that whatever properties we derive are valid for any random sample of the regressors. Okay, this is actually a more modern way to show the properties of the OLS estimator. And also, we're not going to assume normality. So before we assumed the residuals were normal, now we're not going to assume that. We're going to get normality from a central limit theorem. Okay, this is the model notation that we had. It's the same notation we had earlier. We're going to show unbiasedness, consistency, and asymptotic normality, all allowing the regressors to be random. Stochastic means random. Okay, these are the assumptions we're going to impose. Okay, this is called a conditional mean assumption. E of epsilon given x equals 0. Okay, now since x is a random variable, we're going to assume E of xi prime exists, that the inverse exists, and then E of epsilon I epsilon j given x equals 0. So there's no correlation across different observations, and we'll make this assumption, which is that the epsilon is homoscedastic. First, let's look at unbiasedness, okay? The expectation of beta hat. So here we plug in for beta hat, okay? And to analyze this, we're going to have to use something called the law of iterated expectation, okay? So this expectation is over x and epsilon, because they're two random variables. X is random and epsilon is random. So we're taking the expectation over both. What we can do is break it down. First, take the expectation over epsilon given x, and then take the expectation over x. Okay, so here we broke down the expectations. And the next slide will kind of show why that's valid to do this. Okay, then this part, given x, anything containing x you can pull outside this expectation, because given x is like information that is known. So that means, we're taking the expectation of epsilon given x. So anything involving x we can actually pull outside. Okay, that's what I've done here. Okay, so this equals this. I just pulled everything involving x outside. But we're still left with this E of epsilon given x here. This is going to be the identity matrix, so this is just beta. And then this term equals 0 by assumption, right? We assume this term equals 0. Okay, let's look a little more closely at the law of iterated expectations and how it works. Okay, in the above derivation, we used this. So we said this is the expectation over x and epsilon, and we're going to break it down into the expectation over x and the expectation over epsilon given x. Why is this true? So let's look at xi epsilon I. So this would be two integrals, one for epsilon, one for x, right? Now, and this is the joint density. So you can break up the joint density into the conditional density times the marginal density. Okay, that's just a property of densities that we can write the joint density this way. Okay, so let's write that this way. And now, since this integral here is over epsilon, anything involving just x we can pull out. Okay, so these brackets are basically, these are the terms involving epsilon, and the rest we've pulled out. Well, this term inside is E of epsilon given x, and that equals 0 by assumption. Okay, so this is just basically, showing what we're doing when we apply the law of iterated expectations. It really just follows from property of densities. Okay. So now let's look at consistency. So we showed unbiasedness. So we're going to have to use another property to show consistency. Okay, we're going to have to assume that this limit, so this is x prime x, we're writing in the summation notation, and we're going to assume that the probability limit of this object exists, and it equals m, okay? And we'll also assume that this is actually invertible. That was on the previous slide, right? That this exists. Okay. Let's see. Okay, so we can write beta hat OLS minus beta as x prime x inverse times x prime epsilon. So now we convert these to the summation form, and now we can apply law of large numbers to each of these terms. Okay, so this is going to go to the expectation, and then inverse we're applying Slutsky. Okay, and this is also going, or actually the Man-Wald theorem, I think. What did I write here? It's the Man-Wald theorem we apply here. P-lim of a continuous function is the continuous function of the P-lim. And then this term here is also going to go to its expectation. Okay, and then, so this goes to its expectation, and we're assuming it's invertible, so that's like M inverse. And this goes to its expectation, and then applying the law of iterated expectations, again, you know, here, we get that that equals 0. Okay. So we're applying, to each of these terms, we're applying the weak law of large numbers to conclude that they go to their expectation. Okay, so this is just saying that the conditions to apply the weak law of large numbers are satisfied. Okay. So, I mean, I guess this is actually technically Man-Wald theorem, because they're both converging in probability here. Okay, we apply Slutsky theorem next, actually, in showing the distribution. There's another way you can show consistency of beta hat OLS, and that is by showing convergence in mean square. I think that that might be a problem at the end of the chapter. You know, because remember, mean square convergence implies convergence in probability. So you could do it either way. All right, so we did unbiasedness and we did consistency. Now let's obtain the distribution of beta hat OLS. So if we multiply by root n here. Okay, and we're going to show that this is normally distributed. And the way we're going to show this, so this is going to, we're going to apply weak law of large numbers. So this goes in probability to the expectation. That was like that M inverse. And this term here, we're going to apply central limit theorem to this term. Okay. And the central limit theorem, applying the central limit theorem, the mean is 0. So because E of epsilon given x is 0, so by law of iterated expectation, this mean is 0. Now the variance is going to be like E of xi epsilon I squared xi prime. Well, E of epsilon I squared is sigma squared. Or, well, actually, you have to apply law of iterated expectations here too, because you've got E of xi epsilon I squared xi prime. And that expectation is over x and epsilon. So then you write it law of iterated expectations so that you have E of the epsilon I squared given xi. Okay, and that's what we assumed was equal to sigma squared. All right, so that's going to be the distribution of this object. And now it's where we have to apply Slutsky, because this converges in distribution and this converges in probability. Okay, so the overall term is going to converge in distribution by Slutsky theorem. Okay, and so basically we're going to get like this, and then this, and then this prime, you know, because it's like a quadratic form. So we get, and then two of these cancel. So the overall distribution is this. Okay, it's almost the same as what you get when you have the non-stochastic regressor case. Okay, it's just now we have this expected value xi prime, right? Since we're treating x as a random variable. Okay, so that's the last slide. This was a pretty short chapter.